All right, well, this is the second video for lesson 4.2 in our textbook on inverse functions. In this video, we're going to look at how a graph of a function compares to its inverse and look for some patterns with that. Okay, so let's first start out. We're going to look at this function right here, f of x equals, okay, so we are going to find the inverse of f of x equals x cubed plus 1. So it might be helpful, instead of writing f of x, to write y here. And then we're going to follow these two steps. So we're going to interchange x and y. So we have x equals y cubed plus 1, and then we're going to solve for y. So you subtract 1, and then to undo cubing, it's kind of like undoing squaring. You're going to do the cube root. So I'm going to take the cube root of x minus 1. When I take the cube root of y cubed, they're inverse operations, so they cancel each other out. So your inverse, which in this case is actually an inverse function, is going to be the cube root of x minus 1. So notice in the original, you cube the x, then add 1. In the inverse, you subtract 1 and then take the cube root. Everything is the exact opposite operation in the exact opposite order. So let's look at how the graphs compare between these two functions. So if I graph x cubed plus 1, remember we just graphed these parent functions. X cubed plus 1, well, let's just look at what x cubed looks like. It goes 0 cubed is 0, so remember the parent function for x cubed. 1, 1 is on the graph, 2, 8, and then the opposite is actually an odd function, so looks something like this, but then, it doesn't all fit on one page, unfortunately. But then when you add 1 to that, so it's x cubed, it's not just x cubed, it's x cubed plus 1. All of these points move up 1. And so the points, some points on the graph, so this is what you kind of want to do, is you want to look at some points that are on the graph. Instead of 2, 8, we have 2, it's supposed to be up here at 9, 2, 9. When you cube 2, you get 8, but then you got to add 1 to that, so it's 2, 9. And then instead of 1, 1, it's going to be 1, 2, because the y-coordinate gets shifted up. 0, 0 becomes 0, 1, and this point is negative 1, 0, and then we have another point down here. Instead of negative 2, negative 8, it's now at negative 2, negative 7. So when I graph the inverse, remember that inverses interchange all of the xy ordered pairs. So that's what we're going to do to graph this, to graph the inverse. So instead of 2, 9 being on the graph, it's going to be 9, 2. I did not change colors. Okay, 9, 2 will be on my inverse function. Instead of 1, 2, it's going to be over here at 2, 1. 0, 1 is going to be 1, 0. Let me write these out. 9, 2, 2, 1, 1, 0, 0, negative 1. And then remember we had negative 2, negative 7, so it's going to become negative 7, negative 2 on the inverse. So we interchange all of our xy ordered pairs, and that's what the graph looks like. And because we're interchanging all of the xy ordered pairs, what happens is this becomes the graph of, it's going to be symmetric about, hang on a second, let's see if I can do this here, about the line y equals x. So you have, for any inverse, you will have between a function and its inverse, you're going to have the line y equals x as a line of symmetry for the graph. So, like if you folded the red graph over that blue line, it would line up, it's supposed to line up exactly with that green graph. And my graph might be off slightly just because I didn't graph too many points, but hopefully you get the idea. So, a function, add this in your notes, at the graph, I should have said the graph of a function and its inverse will be reflections over the line y equals x, which has a y-intercept of 0 and a slope of 1. So it's that diagonal line, like a 45-degree line. So if you knew just what the graph of an inverse looked like and you didn't necessarily know the equation or any points, you could kind of try to graph it by reflecting those points over that line. But what you really want to do is if you have some points that are on the actual function, remember to just interchange the x, y ordered pairs and plot those points and then try to draw it with as much symmetry as you can. Okay, so if we look at another example here, let's say that our original function is y equals x squared, which recall is a parabola, 0, 0s on the graph, 1, 1, 2, 4, and then that is reflected, 3, 9. Those points are reflected over here. We have a parabola. And if I graph the inverse, the point 0, 0 will, if I flip x and y, it becomes 0, 0. 1, 1 is still 1, 1. But 2, 4 is going to become 4, 2. And 3, 9 becomes 9, 3. And then over on the other side, I have this point right here on the original. Let's write these ordered pairs out. This point is negative 1, 1, negative 2, 4, and negative 3, 9. So if I plot those points, flipping the x and y, or interchanging x and y, negative 1, 1 becomes 1, negative 1. Negative 2, 4 becomes 4, negative 2. And negative 3, 9 is 9, negative 3. So if you graph the inverse of y equals x squared, that graph is not a function. So the inverse, when you interchange x and y to find the inverse, when I take the square root, I have to do plus or minus the square root of x. This top part up here is positive square root of x. The bottom part is a negative square root of x. And if I look at this, my green graph is not a function because it doesn't pass the vertical line test. So the inverse of y equals x squared is actually an inverse relation, it's not an inverse function because it doesn't pass the vertical line test when you graph it. So it's called an inverse relation versus an inverse function. In order for a function to have an inverse that is also a function, the graph of the original, the red graph here, has to be it has to pass what's called the horizontal line test. The original function has to be what's called 1-to-1. So a function will have an inverse function if and only if the original function is what's called 1-to-1. So what does that mean? Well, a 1-to-1, a function is an equation or a relationship where every x has only one y, and it has to pass the vertical line test. Well, if a function is 1-to-1, we're going to add to that it has a parameter that has to have, it also has to pass what's called the horizontal line test. So if it's a function, the original, every x has only one y, and it would pass the vertical line test. If it's 1-to-1, then we have to add, and every y has only one x associated with it. Oops, every x has only, that's supposed to say only one y. And every y has only one x if the function is 1-to-1. So the horizontal line test. So let's say you have a function. I'll draw a couple of them here. Here is a cubic, looks like maybe a cubic polynomial. It's a function because it passes the vertical line test. So So any vertical line that I draw passes the graph at most once. That's what makes it a function, but it's not going to pass the horizontal line test. The horizontal line test is very much like the vertical line test. If I draw, hang on a second, if I draw any horizontal line, if it's 1 to 1, it can only pass through the graph at most once. And you can see clearly that this passes through the graph 3 times. So this is not a 1 to 1 function because it does not pass the horizontal line test. And you can call it HLT for short if you want to. Let's do another graph that looks maybe something like that. This is 1 to 1 because any vertical line I draw passes through the graph at most once. Same thing for any horizontal line that I draw. It crosses through only once. So this green graph passes the horizontal line test and the vertical line test, therefore it is 1 to 1. And therefore its inverse will be a function. All right, that's it.